Hi everyone, I'm Evangelia and I'm going to present our EC paper on Prophet Secretary against the online optimal. This is joint work with Paul Dütting and Yifeng Teng, who are at Google Research, Rojin Rezvan, who's at UT Austin, and Alexandros Tsigonias-Dimitriadis, who is at the Universitat de Chile. So I'm going to start by introducing a related problem, which is the profit inequality problem. So in this problem, we have n different variables. We know their distributions, but we don't know the realizations of the variables. And they're given to us one by one. And at every step, we have to either select the value that we see or irrevocably discard it, and we cannot choose it again. And the goal is to find the maximum one, maximize the value that we choose at the end. So for example, here, maybe I see the first two and I decide to stop at the second one. So my value is 13. But the overall optimal, if I had seen everything, would be 42. So this is our benchmark. It's this benchmark is called the prophet. It's someone who knows exactly the values realized. And this is who we compete against. So the problem we studied is called prophet secretary, and it's a variant of the prophet problem. The main difference here is that instead of having someone give us one by one the values in an order they choose, now we just see a random permutation of these variables. So as you can see here, like this is a random permutation of the variables, and again we see them one by one. So maybe we see this 24 first, then 17, and we think, okay, maybe I should continue. And maybe I see 35, and I'm thinking, yeah, this is good enough. I'm gonna stop and take this. But again, maybe the optimal was later in this order. So what do we know so far about this problem? This was first studied by Evangelia et al. in ESA 2015 paper, and they gave an 1-1/E approximation. Later, some other follow-ups on this saying used different algorithms to get the same factor. Then Azar et al. First improved it slightly 2018, and then up till very recently, the best factor we knew was by Correa et al., and it was 669. But this summer there's a paper on arXiv that gives a better factor. This is 0.67. And on the other hand, we know that we cannot get the actual optimal. And the current best so far is that we cannot do better than 0.7235 of the optimal. So this is the landscape for the prophet secretary problem against this prophet benchmark. So what we asked is, okay, there is this online optimal benchmark, which is basically someone who has the exact same information as we do at every step. So they don't know the future like the prophet. And this optimal is basically a dynamic program where at every step I'm seeing the current variable, the value that I see, and there are some variables that remain in the problem, and I know that they're going to arrive in a uniformly random order. So at every step, I have to make a decision to either stop or continue and get the expectation of the sub-problem. So note here that this is basically a threshold policy where I stop whenever my value is more than my threshold, where the threshold is this sub-problem, the sum of the sub-problems. So in contrast to the prophet, I mentioned that this online optimal just knows what we know. So the prophet knows everything, and this is why it's a very pessimistic and kind of not very realistic benchmark, right? They know the future basically. And also there are many problems that use the online optimal as a benchmark. And recently there has been some work on matching and profit inequalities. And basically every Pandora's box type problems use this benchmark because this is how Pandora's box was actually defined. So our results are, we asked the question, what happens if we compete with this online optimal for prophet secretary? And the answer is that we can compete, and we can get a PITAS actually, which means that we can get an 1 minus epsilon approximation, so arbitrarily close to the optimal, in running time n to some function of this accuracy epsilon. So before I describe the pitas, we have this intermediate step, which is a q pitas. And this is the same, so we get an 1 minus epsilon approximation, but the running time now, the exponent in the running time also depends on polylog factors of n. So we get the runtime n to the function of epsilon times polylog n, which we don't get for the pitas. But I'll start with this and then move to the pitas. So let's revisit our optimal. I mentioned that this online optimal is basically a dynamic program. So someone might ask, why don't we just run this DP and this is the solution of the problem? The problem is that if you do the math, this DP has size n factorial, which is basically the number of different permutations. And this is too big, right? So the key observation was that if we imagine if we have a constantly different distributions or types of variables, then the size of this DP becomes polynomial. And let me elaborate on that. So now let's say we have G different distributions for our variables. Now we only need to keep track of how many variables remain in every group. And again, the DP has a very similar structure, right? We still take the maximum of what we see now, which is this X, and the expected gain from the subproblem. But now the subproblems are not too many because we don't have n factorial permutations. We just have to account for all different groups. And yeah, again, if you do the math, the size of this DP is n to the G. G is the number of groups and n is the number of variables. So ideally, we would like G to be constant, and this is what we do for the pitas. But if G is constant times polylog factors of n, this is still okay for a q pitas. So you can think of, like, there is a trivial way to group everything, right? We can just say everything has the same distribution. The problem with that is that the expected gain would be too low. So what we want is to discretize the variables into G different groups. So we want a few groups, but at the same time, we want the expected gain to not degrade too much by doing this. And we're going to start with a special case for the q pitas. So let's say that all our variables are binary, meaning that they are either VI with probability PI or zero otherwise. So these variables all have different distributions. They're not the same, but they have this bit structure. And we begin with, we have this initial instance with n different distributions. So for the first step, this pre-processing step, we will remove the low value variables that do not contribute too much. And we do so by not losing too much again. Then we're going to discretize the variables that remain. Basically, we round the probability, the PIs and the VIs of the variables into not too many groups. And then we can run this group DP, which runs in polynomial time. And we show that using these thresholds in our initial problem, in our initial DP, then we're not going to lose too much. And let me elaborate a bit on each of these steps. So for the pre-processing step, we can imagine this graph here on the right, where the x axis is the probability and the y is the value. So every variable has a point inside this graph somewhere. So as a first step, we first scale the optimal so that the expected max is 1. And by doing this, we have this area here where variables that have too high value and too high probability cannot exist, because otherwise the optimal will be more than 1. Okay, so we're done with those. This is not a valid area. And then we're going to remove all the variables that have value less than epsilon, or where their expectation is less than epsilon over n. And basically, I'm removing this gray part of the graph here. Everything that falls in there, I'm just going to treat it as it's being a 0. And by doing this, we show that we don't lose too much. And we didn't create any groups because we just forgot about some variables. This is the pre-processing step. And now for the discretization, we're going to deal with these other two cases. So for case one, everything that has probability between epsilon cubed over n and 1, and everything that has value epsilon between epsilon and 1 over epsilon squared, I'm going to round the probability and the values to the closest powers of 1 plus epsilon. And for these variables here, I'm going to collapse everything to have the same value, which will be Vmax, the maximum possible, and then rescale their probabilities to maintain their expected value. And then I'm going to, again, round the probabilities to different groups. So now I lost the factor of epsilon squared. And now I created different groups because I rounded the probabilities and the values, and these create different groups, but the groups are not too many. They're logarithmic in n and a function of epsilon, which is fine for the pitas, for the q pitas. So putting it all together, the idea is that now that we have not too many groups, we're going to run this dp, and the runtime will be this. And we take the thresholds, we put them at the initial problem, and then in the end, we lose a factor of epsilon. So this is all very nice, but this is only for the special case of binary distributions. So what happens for the general case? So the idea is to first generalize to constant support. And then from that, we can use this constant support case to solve the general case. So the general case is going to be reduced to the constant support case. And what do I mean there? So constant support means that every variable looks like this. I have C different potential different values, and C is a constant. So now let's say again, let's look at this graph here. Every variable now has a value probability, has at most C value probability pairs that fall somewhere inside this graph. And the grid is basically the rounding. So I'm going to discretize again the values and the probabilities. So the idea is that after the discretization, every variable that has the exact same points as another one they are exactly the same. They have the exact same distribution, right? So for example, x1 and x3, they're not the same at the beginning, but when I round the values and the probabilities, they are going to fall in the borders of this grid somewhere, and they're going to fall in the same borders because their points belong in the same squares in the grid. But x1 and x2, they don't, because this point here and this point here is different for x1 and x2, and they're going to fall into different grids, basically, into different squares in the grid. So the idea is that if, let's say, k is the value of these value probability pairs, the idea is that when we have a constant support, then the total different groups are not too many. They are k to the c, where c is a constant. So now I have a number of groups that's kind of okay, and I can run my dp, and everything works fine, because this is polynomial. So for the general case, the idea is that we want to reduce to the constant support case. And to do this, we need constant support for the values, right? But now our variables can have any support value. And the idea is that the key idea here is that, again, let's look at this graph. So this is for one variable. This variable can have values anywhere on the x-axis, which is the value. So the idea is that first I throw out everything that's below epsilon. I treat this as a 0. And then every value that is above 1, I'm collapsing it to one single point that has value, the conditional expectation of x being more than 1, and probability, the total probability mass above 1. So this is one single point. And now I can discretize everything between epsilon and 1. And this is a number that only depends on epsilon. So C can be this number, right? It's exactly this number. And now I'm back to the constant support case, where, okay, this constant now depends on epsilon, but it's still a constant. So again, I'm getting a runtime n to some function of epsilon and c, which c also depends on epsilon here, times some polylog factors. So that is the general case for the q pitas. And let's move on to the main result. So for pitas, we don't like this dependence on n that we have in the exponent. And this comes from rounding the probability, the probabilities of the variables. So it turned out that it was kind of tricky to get rid of this. And we use a technique called front loading. Let me describe what we do. The general idea is the same. So we still, again, have the initial instance. We're going to do some pre-processing, which is very similar to the QPitas. We are removing the low value and low probability variables, and then discretize the variables that have higher probability, because this discretization will not depend on n, so that's fine. And the main idea is that for these values that I left out, I'm going to for every support value, I'm going to split the instance into blocks. So fix a support value v. I'm going to split the instance into these imaginary blocks. Like these don't exist actually. Every block has a number of variables inside it. And the idea is that at the beginning of every block, I'm going to flip a coin to decide whether to accept this value v or no. So instead of making a decision at every step inside this block, at every variable I see, for this support value, I'm going to defer to group all of these decisions and put them at the beginning. And then I won't have to decide anymore throughout this block. So this greatly reduces the number of groups that I have and the number of decisions that I make. That's the idea to get rid of this log n in the exponent. And I do this for every support value. So after I do this, then the groups are not too many. And I can, again, the idea is the same. I can still run this group dp and use the thresholds in my initial dp and only lose polynomial factors of epsilon. And the runtime is actually n to the 1 over epsilon to the poly 1 over epsilon. So to summarize, we studied the Prophet Secretary problem against the online optimal. And we first gave a QPitas, which means a 1 minus epsilon approximation in time n to the function of epsilon times polylog n. And then we improved that to a pitas, which is our main result, where the time dependence doesn't have log n in the exponent. Thank you for watching this talk. And if you have any questions, feel free to contact any of the authors.